right? For x is 0. Then you have here E is equal to 2k QR over L. If everything disappears, you just have square root of r squared cosine squared, that's r cos theta. And then this will disappear, this will disappear. You have r squared to the 3/2 power, which is r cubed. D theta, 0 to pi over 2. Now notice what's going to happen. You're going to get 2k QR over L. R and r cubed is going to be just 1 over r squared. Integral cosine theta from 0 to pi over 2 is just 1. Just 1. So you basically have r cancels. L is equal to pi r, and then you have pi r squared. That was the electric field at the center of the circle. So the equation works for x is 0. Now we could put x is 3, or we could put x is -1, and we could find out the electric field anywhere, right? So if we put x is 3, so we have 2, 9, and then Q was 4 nanocoulombs. So the nano and the 10 to the 9 cancels out. Then L is pi r. That will cancel out with the r here. Then you have integral 0 to pi over 2. The theta square root. I'm going to put radius is 2 meters. 2 squared is 4. So 4 cosine squared theta. Right? X is 3 meters. So that's 9. And then you're going to have here x is 2 meters, x is 3 meters, right? So 2 meters, 3 meters. The radius was 2, x is 3. So we're going to have 6 times 2, 12. Okay, 12 cosine theta. Then you divide that by 2 squared, 3 squared, that's 9. 2 times 3. To the 3/2 power. So on the bottom we basically have 13 plus what? 13 plus 4 times 3, 12 cosine theta. So that part looks like the potential integral. Okay? So we're going to go here. The integral came out to be 0.0733869. You multiply that by what? 18 times 4 is 72 over pi. So same thing. Multiply by 72 divided by pi. 1.6819. So the electric field here is 1.6819 newtons per coulomb. Here, the electric field is 5.73. Does that make sense? Yes, it gets weaker, right? Because the electric field configuration looks like this. Right? So there should be more concentration of electric field lines right here, and then over here they're starting to diverge away from each other, right? Like that. So it gets weaker and weaker. By the time you go out to infinity, the semicircular rod begins to look like a point charge. Now, what should the electric field be when I get closer over here? X equals -1. So let's say I go halfway. So when I put x is -1, what changes? You have here, this doesn't change. You put -1 here squared, you just get 1. Okay? You put here x equals -1. You're going to get 2 times 2 is 4. So you're going to get -4 here, right? You have here 2 squared, 4. -1 squared, you're just going to get 1. And then 2 times 2, -1. it's just going to end up being -4. Okay? So -4. So what's the new integral? Halves power. Okay? So let's change that around, see what we get. Okay, now the integral comes out to be 0.49795. Okay, 0.49795. Now multiply that by 72 divided by pi. 11.41 newtons per coulomb. Okay, so to draw the electric field concentration, maybe I should just erase this, make it even better. Okay, so it looks like the electric field here is stronger, right? 11, then 5, then it gets weaker. So it looks like something like this here. You see? You see? So the most concentrated is, as you get closer, over here is stronger. If you get closer, it's going to get stronger, right? After that, they start diverging away from each other. By the time you get to the center, it's only equal to 5. By the time you get to way over here, the electric field is even weaker. So as over here is going to be the strongest, then it's going to be weaker, and it's just going to keep getting weaker, okay? So the electric field strength is a measure of the concentration of the electric field line. So we can visualize it from that point of view, okay? So now you can see how to do the electric field strength pretty much anywhere along the center axial line of the semicircular rod, okay? Thank you very much.